Hi everyone. In this last video for this chapter, we're going to go over a reaction called Baeyer-Villiger oxidation. So in this reaction, we're going to oxidize a ketone or an aldehyde. So if you have a ketone, what you can do is add peroxy acid. And I'll draw out what peroxy acid looks like. So you've got that oxygen-oxygen bond off to the side there. And you can abbreviate this RCO3H. So that R group could be a methyl group, ethyl. The important part though is that oxygen-oxygen bond. Now, what's really interesting about this reaction is we're going to essentially insert another oxygen into our ketone. So we're going to end up with an oxygen kind of adding right in between the carbonyl carbon and the alkyl group. So we end up with an ester. Now, what if we did this with an aldehyde? So if you perform this same reaction with an aldehyde, the oxygen is going to add in between the carbonyl carbon and the hydrogen. So then you end up forming a carboxylic acid. So notice that the aldehyde is asymmetrical. So we have two different groups on either side of that carbonyl. How did we know that the oxygen was going to add in between carbon and hydrogen? Why didn't it add between carbon and the alkyl group? Well, there's actually this is due to the mechanism that we're going to go through on the next slide. But this is called a migration rate or migratory aptitude. And we'll see what that means in a second. But essentially, we have kind of a ranking of where our oxygen will end up. So if you do have a hydrogen atom next to your carbonyl carbon, the oxygen is going to preferentially add there. And then if you have a, let's say, tertiary carbon or secondary carbon, for instance, an oxygen would preferentially add to hydrogen over a tertiary carbon over a secondary carbon. Next is, actually, secondary carbons are equivalent to phenyl group carbon, so a benzene ring carbon, for instance. And then those will rank higher than primary carbons, which will rank higher than methyl carbons. So just something to keep in mind. Now let's talk about why it's called migratory aptitude. So let's go over the mechanism for this reaction. And I'm just going to use a symmetrical ketone as our example. And I'm going to draw out our peroxy acid. So what happens first in this mechanism is our oxygen on the far right is going to attack our carbonyl carbon and move electrons up to oxygen. So we're going to end up with kind of this long molecule. Let's see. So let's draw our negatively charged oxygen. And we've got those two methyl groups coming off of it. All right, and then let's see, we also have a hydrogen on the oxygen bonded to our ketone. Oh, whoops, I drew one too many lone pairs there. And I'm just going to highlight some of these oxygens so you can kind of keep track of where everything is and, you know, what's bonded to what. Because it can get kind of confusing sometimes. So essentially, I just flipped the peroxy acid so that the purple oxygen is connected to the carbonyl carbon that's connected to our blue oxygen. So hopefully that helps you visualize it a little bit better. In the next step, our yellow oxygen is going to grab the proton that's on our purple oxygen. So we're just kind of transferring a proton over, and that's going to leave electrons on the purple oxygen. All right, so next, we now have a neutral purple oxygen. And we have a positively charged yellow oxygen. Okay, so this next step is going to get a little interesting here. The blue oxygen is now going to move one of its lone pairs of electrons down to create a double bond. And when that happens, we're creating a Texas carbon, right? Now, to alleviate some of that stress, instead of, for instance, just moving electrons over to the purple oxygen, what ends up happening is we're going to perform an alkyl shift. So this is one of our migratory shifts. So let's see, that's going to move over to our purple oxygen. And when that happens, the shared electrons between the two oxygen atoms in the middle, those are going to move over to create a double bond. And then electrons in our double bond to the yellow oxygen will move up to the yellow oxygen. So a lot happens in this step. It's kind of complex. But what we end up with at the end, let's see, we've got a double bond to our blue oxygen with a methyl group on one side, and then our purple oxygen, which will now be bonded to a methyl group on its other side. So let's just highlight those oxygens so we can keep track of what went where. And then I'll also draw a little circle around the alkyl group that shifted. Okay, and then our other product, let's see, we have a carboxylic acid. So the yellow oxygen is part of the carboxylic acid. Now, you might be wondering, okay, we have a mixture of products here. So what are we supposed to do with this mixture? Well, we have an ester up above, and that's our desired product. And then we have a carboxylic acid as a byproduct. And luckily, we can just remove the carboxylic acid using aqueous extraction. So that would probably involve the use of a separatory funnel, for instance, and then we'd use an organic solvent and an aqueous solvent to kind of separate the two. But again, if we go back to that migratory aptitude that we talked about, so in our example, we saw that a alkyl group shifted over in green. But what if that had been a hydrogen? So what if, and I'm just going to draw this in orange here. So what if we had a hydrogen there instead? Well, the hydrogen would have priority, and that would move over instead of that alkyl group off to the side. And then let's say that we had a tertiary carbon versus a secondary carbon. The tertiary carbon would move before the secondary carbon. So hopefully that makes a little bit of sense now that we've seen the mechanism. But let's go over another example. So what if we have a ring system So let's say we're starting with a 5-membered ring and we add our peroxy acid. What do you expect the product to be? This one's kind of tricky. So remember, an oxygen is going to insert itself either on the right hand or left hand side. And looking at our starting material, it's symmetrical, so it doesn't really matter which side it adds to. So let's just say it adds to the right-hand side. Well, we still want to make sure that we have all of our carbons at the end. So let's see, we're going to start, we have carbon 1, 2, 3, 4, 5. And now that 5th carbon is bonded to our oxygen that added into the ring. It's kind of a wonky ring I just drew, but that's okay. All right, so now we have a 6-membered ring with the addition of that oxygen. And this molecule is called lactone. Let's also look at another example. What if we have an asymmetrical ketone, like this one, and we add peroxy acid? We have to decide, is the oxygen going to add to the left or to the right? And this is where we need our migratory aptitude list. So if we go back, looking at our migratory aptitude, we said that the oxygen would add next to a hydrogen first. So that would have priority. We didn't have a hydrogen available, but the next highest priority is a tertiary carbon, followed by a secondary carbon, then primary. And it looks like methyl is has the lowest priority. So going back to our example, we have a methyl group on one side, and then we have, let's see, what type of carbon is on the left? A tertiary carbon, right? Because it's bonded to 3 other carbons. So the tertiary carbon gets priority. So that's where the oxygen is going to kind of squeeze in. All right, so we've got an oxygen atom that has added into the left-hand side there. And let's see, this would be an ester. Okay, so let's do a little bit more practice here. I'm going to give you some molecules, and you have to figure out where the oxygen would add in our Baeyer-Villiger oxidation. And let's see, for our last one, okay, so see if you can figure out what your final product would be and where that oxygen would add. And if you want to pause the video and try this on your own, you can, and then we'll go over it together. Okay. So, for our first reaction, which side would we see the addition of an oxygen atom? The left-hand side or the right-hand side? The right-hand side, because we have a hydrogen there and that gets first priority. So let's just add in an oxygen. And earlier we said that an aldehyde would end up producing a carboxylic acid from our Baeyer-Villiger reaction. So that makes sense. We have a carboxylic acid. What about our second reaction? Where would the oxygen add? Next to the hydrogen again. And again, that makes sense because aldehydes will produce carboxylic acids. All right, what about our last one? Which side will the oxygen add to? So which side has a more substituted carbon? The left-hand side. So the more substituted carbon will win out there. Okay, and we get an ester. So not too bad, right? You just kind of have to remember that hydrogens get first priority, and then we have tertiary, followed by secondary, followed by primary, followed by methyl, which we've kind of seen before. So we just kind of have to remember hydrogen is first in this case. Okay, so that wraps up our chapter on aldehydes and ketones. If you have any questions, please let me know. You can always email me or message me, or set up an office hour using the link on the homepage of Canvas. Good luck!